But what if we have a vector that's not in standard position? How do we find the components of the vector? So let's take a look at a simple example in R2, our two-dimensional space. And say we have a point here. Let's call that point A, and it's the point 3, 1. And let's say we have a point here. That is point B. And that is the point 1, 4. And we are interested in the vector that points from A to B. So this will be the vector AB. And just a word here, make sure you get the order right. AB is not the same as BA, right? BA would be pointing the other direction, from B to A. We want the vector pointing from A to B. Okay, so how do I find the components of this vector? Well, I'm in two-dimensional space, so I know I'll have two components. Okay, so the trick is to break the motion into pieces. So let's first move horizontally here. If I move here, how far am I moving? Well, I'm going from x equals 3 to x equals 1. So that's a total motion of 2 units, and I'm going left. So that's -2 units. Okay? And I could do the same thing here. I'm going from y equals 1 up to y equals 4. So going from 1 to 4, that's 3 units. So the components of the vector are -2, 3. Okay? Notice what we did, and this is a little shortcut here. All we did in both cases is we took the value we ended at, the component we ended at, and subtracted the component we start with. So for x, we want to end at 1. We're starting at 3, right? We're ending at 1. We're starting at 3. So if I do end minus start, it will give me the first component for the x. Same for the y. I want my y component to end at 4. I want it to start at 1. So end minus start gives me the component for the vector. So generally, you want to take each component of the point you're starting from, the point you're ending at. You want to take the end minus the start for each component. We're going to use that several times throughout the semester, so try to remember it. End minus start. The values we end at minus values we start at. In this section, we're going to introduce vectors. Vectors are an incredibly important concept in modern mathematics. We use them all the time in all kinds of disciplines. Linear algebra is the study of vectors and spaces of vectors. So we are going to use vectors for the entire course. To motivate the idea of vectors, let's start with a simple example. So suppose you have a cookie jar, and in that cookie jar you have some cookies. Let's say you're starting with 5 cookies. Okay, so that's the quantity of cookies you have. But then you eat 2 of your cookies. And so after eating 2 cookies, you have 3 cookies left. Now, both of these represent quantities. On the number line, we illustrate them as positions, right? We graphically represent them using positions on the number line. But we could also represent the change in the position. And we can do that with two things. We could do it with a magnitude. The change was 2 cookies. And a direction. In this case, we decrease the number of cookies. And so -2. So we lost 2 cookies. Notice this is a different idea. Even though we represent it with the same kind of number, it's just a number, just like the 3 and the 5 were. But it's representing a different idea. Whereas 3 and the 5 represented quantities, and we illustrated them graphically as positions on the number line. This -2 represents a magnitude, an amount, and a direction. How much is the change? And these two things together, magnitude and direction, give me a vector. A vector is a magnitude and a direction. Notice in particular, it is not a position. And I don't represent it as a position graphically. What that means is if I draw an arrow that's 2 units long going to the left over here, then that represents the exact same change, doesn't it? I'm losing 2 units. In this case, I'd be subtracting 2 cookies going from 8 to 6. Because the change is the same, this vector here and this vector here are the same. It doesn't matter where I draw them. A vector is just a magnitude and a direction. Here, these 2 arrows, they have the same magnitude. They're the same length. They're pointing the same direction, and therefore they are the same vector. They are communicating the same change from wherever they start to wherever they end. The change is the same, even if the position is different. So this example applies to one-dimensional space. We could take the same idea and apply it to higher dimensions. So let's look at two-dimensional space. So let's consider the coordinate plane in two-dimensional space. A vector in two-dimensional space has the same properties. It is a magnitude with a direction. The big change here is we just have more directions we can point in. So for example, let me draw this vector here. Okay, so that vector has a magnitude. The length of the arrow illustrates the magnitude, and it has a direction. In this case, it's pointing to the right and up a little bit, right? Well, I could take, if I draw the same thing here, that vector has the same magnitude, it is pointing the same direction, and therefore it is the same vector that I drew here. These two vectors are the same. A vector doesn't have a position, it has a direction and a magnitude. So there are lots of ways I can draw the same vector. I can draw them in lots of different places. All of these vectors have the same magnitude, the same length, and they are pointing the same direction, so they are the same vector. A vector has magnitude and direction. A vector is a quantity with magnitude and direction, but not position. Symbolically, we can represent vectors in lots of different ways. When writing, we will often represent a vector with a lowercase letter with an arrow above it. So for example, this vector here, I might represent it with a V with an arrow above it. Okay? So that's one way to represent a vector. Ways to represent a vector. Okay, so sometimes we'll just call it a variable name, throw an arrow above it. That's how we'll usually do it when we're just writing it out either on paper or on a blackboard, something like that. Okay, in a textbook, they will often use the same letter but just make it bold. So if they take a bold letter, that also means a vector. Okay, now those are the two primary ways that we will see it in this class. Just know there are other ways that we can see it in quantum mechanics, for example. They may use some kind of notation like this. That also means a vector, although it is a little bit more complicated in that case. Okay? And vectors in higher dimensions work the same. We look at 3 dimensions. We could just represent a vector in 3 dimensions with an arrow. If I take a different arrow pointing in the same direction with the same magnitude, it's the same vector, just positioned differently. Vector doesn't have position, so wherever I position it, it's the same vector. In higher dimensions, in 4 dimensions or 5 dimensions, there are vectors also, but they're much harder to visualize. But there's one special vector that does require a special explanation, the 0 vector. The 0 vector is a little bit weird. It is a vector with 0 length, which means direction doesn't really make sense for the 0 vector because it doesn't have any length to point anywhere. So we either represent it with just a 0 with an arrow over it, or we can use that bold notation. So a bold 0 also means the 0 vector. And then one other notation for vectors. Sometimes we like to represent vectors based on what point they can point from and to. So say we have 2 points, A and B. A vector that can point from A to B, we might describe this vector by saying, hey, this is the vector from A to B, and write a little arrow above it. That's the vector that can point from A to point B.